Let's give a minute or two for everyone to join.
So if people want to ask questions on the way, is there a way for them to raise their hand or something?
I think there's a reaction now there's a reaction on the Discord chat, or they can post a message in the text. If you see the channel name, and next to it there's like message icon. Yep. How are we feeling? Are we ready?
I'm all good.
Good. All right. Okay. Yeah, thank you everyone to join today's learn and share. It's very exciting to have Jeff and Nico walk us through how they build this KCG ceremony. And today will be a very special format, which Jeff will do in the whiteboard and along with Nico. And during the session, I kindly ask you to mute yourself, and you can ask question anytime by posting the text message. And today we are streaming on the Twitch and YouTube. It's the first time we're doing that, so we are also very excited and nervous. So, all right, microphone is yours, Jeff.
Okay. Hi, everyone. Yeah, I'll kind of I'll talk a bit about the history of our involvement and what's going on inside the ceremony and some of the aspects around that, and then Nico will do a walkthrough of the ceremony site and explain some of the details about the building process. So I'm going to be working on the whiteboard, which is one of the shared windows here you can click on, and please ask questions along the way in the chat, and I'll try and keep an eye out for those messages. But just to start off, I think a bit of history about PSE and trusted setups. So for a long time now, we've been running trusted setups, and perhaps the best known one that we run is the Perpetual Powers of Tau, which is a phase 1 Groth 16 trusted setup. And so in Groth 16 we had, for any like production scale zero knowledge based or Groth 16 based system, we need phase 1 and phase 2. So phase 1 is generic Powers of Tau ceremony, and phase 2 is circuit specific. So we also run the phase 2 ceremonies, but our phase 1 Perpetual Powers of Tau is kind of, as the name suggests, it's perpetual. It is still running. If anyone wants to contribute to that, we're taking contributions. We get a few trickling in now and then, but that's a big one that does 2 to the 28 powers of tau. That's got to be bigger than any circuit. The number of constraints, if it's less than 2 to the 28, we can cater for that. So that's a very long contribute and quite complicated contribution. Takes like a day to download and run and upload. So that's a kind of a very involved process. Not everyone find that easy, but what we do with also is phase 2 SNARK ceremonies, which is circuit specific. So we take the phase 1 input, and our phase 1 files have been used in lots of projects. There is as a public good for people to use as their phase 1 strings. Our phase 2, we will run a specific ceremony for the circuits. So this is usually, this is going to be specific to a project. They will have finalized their circuits. Now they need to run the phase 2. So we will trusted setup group. We will provide the software and the setup to do that. We've done trusted setup ceremonies for ZKG, for CLR Fund, for Semaphore. A couple of those have been quite big. Phase 2 ceremony for CLR Fund, we got around maybe 3,500 contributions. At the time, it was record-breaking. May still be, but I think there've been some big ones since. But it's the nature of those is they're able to be done in a browser. So the size of the computation is small enough that once we sort of compile it in WASM and multi-thread and everything, then we can run it within a few minutes. I think the longest circuit for CLR Fund might have been a 10-minute or 15-minute contribution. But yeah, that's the scale we're looking at. So it's much simpler than the phase 1, the big computation. And because we can do it in the browser, we can just write the software and publish a site, and people can join in. It's very easy for people to join in. So it doesn't require any special command line knowledge or installing software. It's just go to the site, click, sign in, run the computation, and you're done. So that's our history in the Trusted Setups group. So we have the software to run that those ceremonies, the phase 1 and the phase 2. It's all based on commonly available software, of course. At the moment, for the browser, the phase 2 for the browser, we're using Snark.js, which has the WASM components built in. It's very easy to integrate in the browser. And it's easy to get that up and running, and it's in recent iterations it's been quite fast. It does the multi-threading, so it's fast enough for us to run and get a fairly quick contribution time. Contribution time varies, of course, a lot. Depends a lot on the amount of hardware you have on the device you're doing the compute on. And so someone with 16 cores is going to be much faster than someone with 2 cores, and someone with a 10-year-old laptop may be quite slow. But we get all sorts of variations, and we sort of have an upper limit. So if you're too slow, then you might miss out. But yeah, so that's our software. And fast forward to about a year ago, a bit later than that, perhaps. The Ethereum research group started developing plans for their for EIP 4844. So EIP 4844 is proto-danksharding. it's a proposal to provide data availability sampling for so that layer 2s can provide a very succinct proof for the data that they're rolling up onto layer 1, and that's going to improve the economics for layer 2s and rollups. So it's really it's quite an important milestone for Ethereum that's coming up, and the scheme they've chosen to use for data availability sampling is KZG commitments, KZG polynomial commitments. Ooh. I was trying to type that. Never mind. So yeah, so that's why that's where the KZG comes into it. KZG is a commitment scheme, and it will provide a succinct proof of the data that's being sampled. And the catch with KZG is it needs a trusted setup. That's it. The research group realized they needed to plan a ceremony to run this trusted setup. The result is going to be baked into the Ethereum core to prove these commitments. So it needed to be rock solid, bulletproof. We need to be able to demonstrate to future generations, future users of Ethereum, that we have a secure foundation for these commitments, and the trusted setup is a key part of that process. So they started planning a ceremony, and the first step was planning out whether it could be run in the browser, whether it could be how many people would involve, what's the complications of running a big ceremony like that. So because of our experience with running ceremonies, we were asked to do a little proof of concept, and we could do that with our existing trusted setup ceremony software. We were, the software was written for snark snark proofs and snark ceremonies and Groth 16, but it's fairly easy, as it turns out, to adapt that to the trusted setup that KZG needs. The actual trusted setup that KZG needs is powers of Tau. So it's a very simple powers of Tau, and it's I was trying to type that. Never mind. So it's like the actual computation is similar to Groth 16 powers of Tau, but a little bit simpler. And the simplification is the snark. The powers of Tau ceremony for snarks, I'm talking about the phase 1, is powers of Tau plus a few extra factors that are used in the zero knowledge side of SNARKs. There's no zero knowledge component in KZG commitments. It's all transparent. So those extra factors aren't needed. But it turns out they're not a big deal in the scheme of things. If we ran it with those extra factors, we could still gauge the the feasibility of running a ceremony in the browser. The other advantage we have, Charlie, I'm just going to try and type some things, or maybe draw. Okay. The other advantage we have in this is that when we're dealing with SNARKs, the size of the ceremony is proportional to the number of commitments. So if you have a million commitments, what's that, 2 to the 18 or something? You're going to have a fairly big computation, and if you can whittle it down to 200 or 300,000, it's going to be a lot more manageable. Now, so yeah, a million is about 2 to the 18, roundabout. What they're planning for the KZG ceremony, we have 2 to the 12 is the base requirement, but they figure to allow for extension or future expansion, they will have 2 to the 13 powers and 2 to the 14 and 2 to the 15. So they want to run those four computations, but the highest is still 2 to the 15, which is like 32K. So it's still not too big. So yeah, back to the planning process. We were asked to do the proof of concept, and we could adapt our software. So just tell it to us to run 2 to the 15 powers, or actually 2 to the 16, because you add up all those ceremonies and it's almost 2 to the 16. So that gives us a gauge of how long the whole thing would take. We had so we had our software that was able to run, that had SNARK.js inside it and could run a phase 2. We adapted that to run these 2 to the 16 powers of tau in a SNARK.js, in a ceremony that's suitable for SNARKs with those extra factors, but turns out it's not such a big deal. The other factor is the KZG, the curve they've chosen to run off is BLS 12381, which is different from what we use in SNARKs, right? So that was the other thing we had to change to run this test proof of concept ceremony. Turns out that SNARK.js you can switch curves pretty easily, just a parameter. They've written the software to allow either curve. So for us to run that proof of concept, it was really just change the parameters inside parameters that we're calling SNARK.js with, and spin it up. So we did that. We did a few proof of concepts. We were aiming for a contribution of about 1 minute average contribution time. A couple of minutes would be okay, 2 or 3 minutes. 15 minutes, you're starting to get a bit awkward. Probably still manageable, but at least we had an idea, and it turned out to be about a minute or two in that Snark.js implementation. So that was looking pretty good. Looked like we could package this software into the browser and run that size of ceremony. And so that gave us a basis on which to plan to map out how we would run a large-scale ceremony. That was all using demo software, of course, or proof of concept version. I'm just pausing to look at a question. When the ceremony finishes, the SRS is produced. How is it stored so it is not revealed? So how is it possible to use the number in the client? Yeah, good question. I might talk a bit about that. Yeah. So yeah, I think I'll delve into that a bit. So let me find a different place to draw. So yeah, the powers of Tao ceremony. The basic mechanism is that a computation happens in the client's system. That involves generating some entropy and coming up with a secret. And that secret is used to combine with everyone else's secrets in a way that it's never revealed, it never leaves the client. So that's a really useful cryptographic trick that is the basis for everything we do in the blockchain world and broader cryptographic world. We have so we have a secret, and we're doing elliptic curve cryptography to make that a public. We have our secret key, so with the elliptic curve cryptography, we make it a public key, and that's in a way such that you can never go back from that public key to the actual secret that was used to derive it. This is familiar to all of us in using our private keys and making our public keys and our Ethereum addresses. So it's the same process that's used in Powers of Tao. So I'll delve into that a bit more. The other notable thing about these trusted setup ceremonies is the security basis is that if one person manages to keep their secret a genuine secret and actually discard it, so that no one else learns about it, then the whole ceremony is secure. So let me explain why that happens. So we have a secret, and if we multiply that by the elliptic curve factor, we call G1, we end up with a public key. And that's an elliptic curve point. So yeah, there's an elliptic curve at the basis of this, and that's just a point on the curve. And you can never work back. The secret itself is just a number, scalar number. So you can never work back from that point on the curve to the scalar that was used to derive it. That's the basis of the mathematics we're talking about. Now, if we're in the trusted setup, what we have is Alice. We have Alice and Bob and Charlie. They come along and want to do their contribution. So the first one in line is Alice. So she will have her secret. We call it SA. She will derive a secret with some sort of entropy deriving process. Nico will talk about our methods a bit later. And she will derive that secret in the privacy of her own browser and then mix it with the curve G1. That's a 1. And we end up with public with the public key that results from Alice's secret. And then Bob comes along. So Bob's secret is SB. Now, Bob doesn't know Alice's secret. So we can't, what we're trying to end up with is SA times SB times G1. And we have a new public key. Bob doesn't know Alice's secret, but he does know PA, the public key for Alice. And simple mathematics, it works in elliptic curve cryptography as well as it does in basic mathematics. SA times SB times G1 is the same as SA times G1. So, which is PA. So all he has to do is multiply PA times his own secret and end up with PB, and that all works. So so as we see, if Alice keeps her secret private, and Bob will never learn that secret, and the result is PB is a public key that can never be rederived. Alice doesn't know Bob's secret. Bob doesn't know Alice's secret. They both throw it away at the end of the ceremony if they're doing it correctly. So there's no danger that someone might discover it in the future. And there we have it. Result that as long as one person keeps their secret, so even in the scenario where Alice she got bribed and she sold a secret to someone who was trying to collect all these secrets. Then Bob resisted the temptation and actually managed to keep his secrets a secret and discard it. You still can't derive, you can know all the other points, all those other S secrets. But if you don't know Bob's, you still can't derive that final public key. So that's the basis for that claim that as long as one person keeps their key private, then the whole ceremony is private. So that's when we're running the ceremony, Alice will derive her secret. She will mix it in with the elliptic curve point and produce that public key that results from Alice's contribution. And then she makes that public. It goes to the central sequencer, we're calling it, who then passes it on to Bob. And Bob just sees that public key, mixes it with his own secret, and produces the next public key in line. So what's actually going on with powers of tau is tau. Let me get the pen. Tau is the mix of all these secrets, the multiplication of all these secrets. And the idea is that no one should ever know what the private value of tau is. We only know the public value once it's mixed in with the elliptic curve points. So it's made into an elliptic curve point. And the actual ceremony, you compute tau, you compute tau squared, compute tau cubed, and so on up to tau to the 2 to the 12. Whoops. So you have all those points, and that's what the computation is all about. And then you just package that into a JSON structure and hand it back to the sequencer, and they do a bit of validation, pass it on to the next person. So as you see, as a result of that, the computation needs to be run one person at a time. They need to complete it, hand it over to the sequencer. Sequencer will do a quick assessment for validation, but of course the sequencer, you'll see that all the secrets, the entropy that's generated and the secrets that are derived remain on the client side. Sequencer is never is only in possession of public information. So the sequencer has very little power. A lot of the time that role is called a coordinator, but we simplified the name. We thought the name might suggest a little too much capability, too much power. So we changed the name to sequencer to suggest that it really is just a very mechanical process of receiving a contribution and doing a quick validation and pass it on to the next person. There's no sequencer can't. Well, they can do. They're never in possession of those secrets, so they can't divulge secrets. They can do tricks like they could censor entries, declare them invalid when they're really not. So there's a few security aspects to the sequencer role that we need to be mindful of and cater for. But most of the actual security is guaranteed on the client side, and as long as the software we produce will faithfully not divulge those secrets, and will actually delete them when the computation is done, then that's a key part of the security of the overall thing. Yeah, so I think that so the result is called a SRS, a structured reference string. It's really just that package of that array of taus, all the powers of tau strung together, and then it's going to be stored in some public place. It might be I don't know if it's going to be on IPFS or stored in a smart contract or something. But yeah, it will be baked into Ethereum in the case of the KZG, and Ethereum clients will refer to that to verify rollup data. So I hope that explains how the secrets can be made public and the security is still maintained. Okay, just some other aspects of the way this ceremony has been designed. With our ceremony for Snark, we had a system where we would take contributors, we would put them in a queue, we would maintain their position in the queue, and as long as they were sort of well behaved and kept checked in and appeared at the time when they were required to run the computation, then we allowed them to do that. What we thought with the KZG ceremony, we've changed that design a little bit. So we are expecting a lot of contributions. We're hoping for, I talked a bit before about running 3,500 contributions for our CLR fund ceremony. We're hoping to be several times more than that for the KZG. It's going to be running for a long time, a couple of months, maybe. It's very easy to run. It runs in a minute or two, so it's very easy to just a few clicks and you're in, and you wait your turn if there is a queue, and a minute or two later your job's done. So all the factors are there to have a really big ceremony. We started out thinking along the lines of keeping a queue idea. So when a contributor comes to a website and signs in, they join a queue. So first in is the first to contribute. That does require the sequencer to keep the state of every person who joins and make sure they're still alive and online. So we thought there's a simpler way to do that, and that's just to have what we call a lobby. So instead of a queue, just contributors come into the site, they sign in. Once they signed in through the front door, but they're in a lobby, and people are chosen at random from the lobby to contribute. The sequencer doesn't need to track each person in the lobby and track when they came in and allocate it to the first one who came in. Instead, it's just chosen at random. If there's busy times, then the lobby will grow in size. But I think because we're running this for a long period of time, we may not get such busy times. And it's easy for people to come in, and if it's busy, they might decide to come back later. They'll have plenty of time to do that. So it's going to be a lobby. Join the lobby. You'll be chosen at random when your time comes. If there's no one else in the lobby, then you will be chosen. Being chosen just means you receive the previous contribution and you do the computation and hand back your updated contribution. The contribution for the size of the package that's being downloaded and uploaded is about 7 megabytes in this case. So that's pretty manageable. Someone's got a really slow connection, they're going to be a bit slow, but we can sort of have up limits for how long we take, but we can be fairly generous about that because it's a fairly small computation time, and it should allow many people to contribute, even if they're in places where internet connection is not good, or if they haven't got a latest model laptop or desktop. So that's what's going on behind the scenes. Now, let's just talk about some of the attacks that are possible on this ceremony and how we defend against them. So one way to attack would be to harvest all these secrets. Now, you can do it by bribery, by bribing each contributor and buying their secrets, or just have some mechanism of some side channel attack that harvests the secrets and phones them home. What our main defense against that is to have many contributors. So it's all very well if we had a dozen contributors, it'd be fairly feasible to imagine someone harvesting those dozen secrets, and then they'd know the Tao that resulted. But if we have 10,000, then that's a much bigger challenge. So that's one advantage in having a small ceremony and making it easy to run is we get lots of contributors. We'll have a few little incentives like POAPs for those who contribute. So that should attract a few more contributors. So that's a great way to defend against this sort of harvesting tax or trying to monopolize the ceremony. There are the other way that someone might try to monopolize the ceremony is to do a kind of civil attack. So we defend against that by asking people to sign in, and you can sign in with an Ethereum address, but it can't be just an ephemeral address that's just been created. It has to have some sort of history, a bit of a nonce, nonce greater than 3, I think is the requirement. So that will limit civil attacks. Still, some people will still have a few accounts that they can sign in with, but that is not a serious breach of security, as long as they don't have thousands or tens of thousands. Or if as an alternative, we're allowing sign-ins using GitHub profiles, GitHub OAuth. Again, it can't be just an ephemeral GitHub address. We do have some sort of checks to make sure there's a history of activity behind that GitHub account. So it's another defense against civil attacks. We could imagine other scenarios where there's like a production line attack on the software, and someone's inserting a bit of software to harvest these secrets and phone them home. So our defense against that is really to have multiple implementations of clients. So what we've done is have an API. It's a pure REST API, just asynchronous communication with the sequencer for everything. Sign in and contribution and waiting in the lobby, and just general retrieving status and so on. And because that's very simple, it's very easy to generate to develop a client, and we're encouraging lots of variations on clients that can do this computation, and lots of variations in entropy generation. It should run on different operating systems, different environments, be written in different languages, use different tool sets in the stack. We want CLI, we want browser. If someone wants to write one that runs on a Raspberry Pi that's isolated from the internet, that'd be great. And after the public contribution phase, there will be a private, or like a special contributions phase for like crazy ideas. Someone wants to derive their entropy from a piece of uranium and with a Geiger counter and throw it in a volcano so it's destroyed after the ceremony. Then go for it. There'll be a time for all those ideas. That's a reference to the ZKG ceremony, which did have very elaborate mechanisms for keeping entropy and contributions secret, and all this. The Tau is the toxic waste, like the secrets are the toxic waste. So yes, Zcash, things were a bit different in those days in terms of multi-party ceremonies, but it's a great story if you if you come across that story, it's very dramatic. Things are simpler these days, and we can run this ceremony in the browser, and we don't need to go to those links, but we will have a phase. It all adds up to more security in the end. So we'll have a phase to allow those sorts of innovative techniques. But yeah, it's pretty easy to make a client. Several people are doing it. The one we're working on will be sort of the one that is published for people to join, but it's only one of many alternatives. Other attacks, we could think about the sequencer. The sequencer could do things like insert its own contributions and then harvest all those. Just keep track of all the contributions. It's faking, and so a defense against that is when you complete your ceremony, you sign it with your Ethereum address. If you're using Ethereum, and your whole contribution is signed so that it's verifiable that it was produced by that address, and in all our public records of the ceremony, that will be part of the published data, so that in the future people can refer back to that and have some assurance that the sequence is not just faking contributions. Sequencer could censor. So there will be a record that we publish on our website. And so that so when you complete your contribution, you can download a little JSON file that records all your signatures and everything, and your public record, and you can track in the published version of the data that it matches that data and it hasn't been faked by the sequencer. And I think another defense will be there will be multiple teams generating the sequencer software and handing over from time to time during the process from one to the other. I think I may have talked enough, and I might hand over to Nico now, if that's okay. Nico? Thank you.
Thank you, Jeff, for your presentation. I think it's really nice to know the background of the KCG ceremony and part of the math that comes behind. Okay. Can I try one last time I will try to put my presentation on the mirror board to see if people can see it. Is it there? Okay, yeah. Okay, so my part of the presentation was focused on 5 points about the practical implementation of the KCG ceremony. So the first thing that we're going to look is how the lobby and all these sequencer and participants interaction happens. Other thing is to see how the contribution file looks like to someone that wants to do their own implementation. How we generate contribution in the web browser, why we do this double signing that it's Jeff already talked about some of the attacks, so double signing help us prevent some attacks, and last but not least, the WASP integration, how we were able to put the Rust code that it's very efficient and very fast to be run in our web browser. So the first thing is what the lobby looks like. The lobby is, so as Jeff was saying, we have multiple participants, and these participants want to contribute their secret, their entropy into the generated SRS, right? And they have to do it in order. So participant number one will go first, the number two is going to be second, and so on and so on and so on. We need a sequencer in order to organize and coordinate this sequence, right? It's not more than that, that the sequencer is just a server that gives participants their time slots. So you go first, then you go second, etc., etc. The contribution, as Jeff said, might take different time depending on the on your machine, on your internet connection, etc. So each participant is going to have a specific time to fetch the contribution, to fetch the whole actual SRS, do their contribution, and then send it back, upload it back to the sequencer. So when participant number one is gonna be doing this, the participant number two is gonna have to go, is going to have to wait inside the lobby. We call it lobby because we put restriction on the number of participants that can be at a specific time. So, for example, right now in this picture, we have a lobby of four. That means that there can be only four people inside waiting and be already assignated a time slot, and then all the other participants, number five and number six, will have to wait until the lobby gets until somebody leaves the lobby, and then the other persons outside can go in and get their time slot, right? We're doing some improvements on the front end to show this better, but that's how the lobby looks like. If you have any questions, please post it on social media, Twitter, or even on the GitHub repo. If you find any issues regarding this or anything else, you're more than welcome to post it on the issues in the GitHub repository, so we can fix it together. How the contribution file looks like. So the contribution file is just a JSON file that has a couple of attributes. So the main components of the contribution file are the powers of tau, that are a lot of X strings that get multiplied by your secret, right? So we also have 4 contributions inside this ceremony. 4 contributions that vary on the number of G1 points. Why we have 4? It's because on the beginning, the Ethereum developers are thinking that the data we're going to use, it's going to be of a specific size, but then it might be bigger, so that's why we are generating all 4 sub-ceremonies, right? When you go into the website or when you build your own implementation, you're going to compute the 4 ceremonies at once, so you don't have to worry about that. But if you are a developer and you want to learn a little bit more, you have to consider that we have 4 sub-ceremonies on this KCG ceremony, right? How we generate the entropy? It all depends. As Jeff was saying, you can have like a lot of crazy ideas on how to generate entropy. You could go in an airplane and take the entropy from the air. You could use radioactive materials, etc. In the web browser, what we are doing is we are catching up your mouse movements. So every time you move the mouse, we are recording your X movement, your Y movement, and the specific timestamp of that period. So unless you are able to recreate that exactly, you will not be able to remember your secret, and the contribution is going to be safe. We also let you input some string that it's going to be encrypted, and it's going to be put together with the mouse entropy to be used as a random seed generator. Why double signing? the other question I had on the board was okay. So this contribution, as Jeff was saying, has a couple of attacks. One of those attacks is that I could say that I am maybe, well, I am Vitalik and I contributed to the ceremony, right? So we have a couple of signing methods that can be used to sign your entropy, and in that case you can really show that you contributed to the ceremony, and it's not someone trying to say, oh, I am that person and I contributed, right? I don't know if that makes sense. Let me repeat again. We are encrypting the public keys of your entropy, of your secret, with your Ethereum address. So in that way, when someone claims that they have contributed into the ceremony, we can indeed prove that the secret, the public key of their secret has been signed with that specific address, right? And last but not least, this has been the most challenging part so far. It was about integrating the Rust code into the browser. So behind the scenes, the people, the core devs, the core Ethereum devs, wrote the crypto library using Rust. We took that Rust code and passed it through WASM-Pack, and then compile it as WebAssembly to be run on the browser. We are using the React framework to build our frontend, and right now the contribution works on Firefox, Chrome, Brave, Microsoft Edge, Opera, etc. Uh, right now, we also want to upload the frontend in IPFS, so you can fully trust that the front end version you are using and where you are contributing is in fact the one that that was already hashed to be uploaded to IPFS. That way, we are trying to do this in the more decentralized way possible. So that's it from my part. I don't know if there are any questions or comments. I will be happy to answer. And Jeff is also here.
Thank you both. Yeah, if you are watching on stream, you can post your question on the text chat. I will carry over here. And if you are in Discord, feel free to mute yourself, ask question. Thank you.
How long the ceremony will be open?
It's going to be a couple of months. It's the times are sort of settling down a bit now. The original idea was to have it running before this, but I think there's been a formal decision not to include the IP 4844 in Shanghai upgrade. It'll be in the next hard fork after that. So we've got a bit more breathing space. Looks like we'll start the ceremony. Look out for it the end of this month, early next month, and it might run for 2 months, 3 months, something like that. It's not on. It's only on test site at the moment. You can actually go to that test site. You can see those beautiful designs. I wish can someone share the screen to show those designs. Yeah, the design thinking behind this. There's been a lot of really beautiful work done on it, and the thinking was taking that notion of a multi-party ceremony. And using that word ceremony, this is going to be a community effort. It's going to be have a sense of ceremony around it. A bit of mystical invocation. That we're producing this public string that no one knows the secret, but we've all had a part in producing it. And yeah, certainly for the security aspects, there's it saying trust no one, verify, don't trust, but if you have trust, then only trust yourself. So yeah, if you want to be sure that this ceremony is secure, then run a contribution yourself. That's the philosophy, and we've tried to make it easy. We've tried to make it a beautiful experience. The design team, really shout out to them. Giali and Trent Van Epps came up with the design and put a lot of work into it. Shout out also to Nico and for doing the hard work of coding all that, and Takamichi for his great contribution. But I'm going to try and share that screen.
I think one interesting question that Charlie made is right now we are in a test ceremony phase, and the thing is that we cannot do it as a mainnet, and we cannot use the testnet results on the mainnet because there might be some people that have already contributed and they want to contribute again. There also might be some bugs that we didn't catch on, and some bad contributions might have passed, right? And that's why we have the difference between a test ceremony and a main ceremony, right?
Yeah.
If you want to demo the website or
yeah, I'll try. Yeah, so yeah, I think the design is just beautiful, and it's quite simple. Are we looking at my screen now? I think so.
Yes.
The entropy collection is done first. It's tracking movements and the secret, and you'll see that snake is tracking the progress of entropy collection. It's usually quicker than that, which is very good on the mouse. Okay, and then that's generated the secret at that point. So now we sign in. I think sign in with Ethereum will handle that. I've just got my MetaMask hooked up to that. Everything's a little bit slow at the moment on the test site. Hopefully it'll be a bit more responsive on the live site. Okay, it's verified my account. You can obviously only contribute once with that Ethereum account. So if I had contributed before, it would not allow me. So I've done the sign in with Ethereum. That's my sign. I'm now doing a double sign, which is I've got my secret. I produce a signature from that secret. Call it a Powers of Tau pub key. And so I'm producing that signature, and that will be part of the record. That will tie my contribution to the Ethereum address that I used to sign in. And that will become part of the record and all be verified back to trace back to me. I've just joined the lobby. There was no one else in there. So I was straight into the computation. And now we have this beautiful shape that's just pulsing to indicate that it's doing the computation. This will take a minute on my laptop.
Um, I have a question. Just kind of curious to know what was the most challenge you guys encountered when you developed this front end?
I think the WASM stuff was quite challenging. Working in Rust, and we're not Rust developers, managed to learn enough that we can package it up and build it in. But yeah, getting that to work with the multi-threading and so on, quite challenging. Otherwise, anything come to mind, Nico?
Right now, we're having some issues with other wallet providers. So MetaMask and Wallet Connect have really nice standards and they work pretty nice. But then you also have another wallet providers that have some tricky things that need to be done for it to fully work. That's another thing that we are suffering. But it has been a nice experience, yeah, overall.
Do we still plan to let people who doesn't have a wallet to contribute, or that was out of scope?
Yeah, if you don't have a wallet, you can contribute with your GitHub. Or if you think the real thinking behind that was some people might, because we need the nonce greater than 3, some people might only have that account on their cold storage hardware wallet or something. So insisting that they come get a cold storage, go into their cold storage, then we can just allow them to sign in with GitHub. That's a reasonable anti-Sybil check, and it still fits the bill. So that's another, that's the other way to do it. Okay, not too sure. My ceremony has finished processing. I'm not too sure why it's stuck, but it basically got through it. The next thing that happens is it shows a record with some blockies that uniquely identify my contribution. So yeah, we're over time now, I guess. Any final questions, comments?
One last one, maybe other people has. So sooner we say it's better to if it will be even more secure if the developer can run this trust app by themselves. Does that mean like a COI tool command line they can run, or what does that mean? Sorry.
I didn't quite catch it, but
I I feel I catch it that Charlie was asking if it will be more secure to use other CLI implementations. Um,
yeah,
it depends on how much you trust us. The repository is public. You can audit it by yourself. We also have an audit report from an external party. But if you want, you can also create your own implementation and contribute. And we will be super happy to help you out because the more different, diverse implementations we have, the better. Yeah, I don't know if I answered the question.
yeah, that's right. Yeah, there's even if we do everything perfectly and bug free and everything, it's still there's still a chance that something sneaks in or a supply chain attack in our software. So other software implementations just add extra security. So yeah, we try to make it easy to do that, and there will be other avenues to contribute and other people developing the clients.
Cool. Any other people have questions? Nico or Jeff, would you mind post the repo link here so people can easily find if they want to report issue or anything?
Yeah, thanks, Nico.
Yes. Right now, we haven't launched the ceremony, so it will be cool for you to test it in different browsers, different things, and please let us know any comments and issues you find. That will be super super helpful for us.
Cool, good to know. Okay, if no one else has questions, and I thank you all to join today's Learn and Share. It was very interesting to learn all the behind scene and thinking build strategy for this ceremony. Yeah. All right. So I will see you next time. Thank you very much. Enjoy your holiday too. Bye.
Yeah, thanks everyone,
Yeah.
and look out
Bye.
for our go live.
Yep. Bye.